Hello, thank you very much for the invitation to this keynote speech, which I have also subtitled as Medical Imaging AI Needs Serious Rethinking and Redoing, as I believe we have significant problems. Um, so here's an outline, why we need major rethinking and redoing, special focus on physician in the loop AI, including active learning strategies, foundation models, opportunities and challenges that exist with them, large data sets, and platforms for AI deployment in the clinical setting, AI as extension of the human being, an important discussion that needs to be happening, and finally, implementation science considerations. I want to really acknowledge both Ferishte and Noor for significant help with creating this presentation. So we have a problem, and in fact, Houston, we have so many problems, not just one. As you will see in the course of this presentation, and we will emphasize, medical imaging data are limited, much more limited for various reasons, for patient confidentiality reasons and other reasons compared to the other kinds of imaging data, natural scenery, etc., that have really created breakthroughs. So it's an issue. Computing power is limited in many of our centers. And a clinician does far more than just do pattern recognition on an image, which is actually a highly problematic assumption that many of us AI developers are having. And so existing models presently do not really perform that well in the medical imaging setting, and something very serious needs to happen. We had an article on a brief history of AI, how to prevent another winter, and we discussed seven serious considerations, one of which I will return to towards the end of the talk on really understanding, or at least admitting utter lack of understanding of what a human being actually does, exaggerated claims, and a number of other things that you can see here. But specifically now, I will be referring to exaggerated claims. So one meaning of exaggeration is to do so in prediction of the future, and we have plenty of that in our field. And we tend to do this a lot. This is partly rooted in excitement that we have, self-confidence, laziness, ignorance, hubris, optimism, and a combination of these things. And so examples of this are, for example, when we have stated in the past, AI developers, that CNN AI was going to replace radiologists. And this kind of a statement was, for example, made uh, um, uh, something like 8 years ago. And of course, this hasn't taken place. If anything, what it has created is a fear in radiologists that they will be replaced, but they certainly have not. And so then the next new frontier exaggerated claim is that foundation AI is going to replace not just radiologists, but humans altogether. And again, this shortage of workforce in radiology, nuclear medicine, other areas is quite an interesting one. But this is quite a surprising thing when these kind of claims are made. And actually, if you look at uh, the mental demand for different disciplines within medicine, you'll actually see that in radiology, there's a very high mental demand. And however, there's this opposite sort of assessment that maybe this is a sort of a simple task. And why is it that people have targeted medical imaging and radiology? Well, part of it is because of something great that's happening in this field, and that is that the data are structured, they're stored in retrievable sort of formats, and standards of truth are there. The physician-patient interactions are more opaque, and basically, we really attribute our understanding of, for example, non-medical imaging fields like satellite imagery, and we extend that as though we really we think we know what a radiologist actually does. So to really summarize the essence of the problem, most medical imaging AI studies presently only focus on images. That's a big problem, and this needs to change. This is a problem of extending from natural scenery AI that we talked about. Um, for example, a natural scene typically is an image. You don't have associated gender for a scene of a forest. You don't have a history of smoking, right? The success of the natural scenario AI has come over, and we think we can just extend that. Whereas for a patient, there is significant other associated clinical and demographic information that we tend to ignore. And the other thing is medical images, though they are commonly quite larger than non-imaging data, are themselves structured, which makes it easier to use. But all this non-medical imaging data, the medical non-imaging data, if you will, they also need to be taken into account. And vast majority of medical imaging AI studies do not at all include that kind of information. And so this also has been true historically for even data challenges and competitions, right? That clinical information was not included. And this really needs to change. And of course, in certain challenges, this has changed. I just want to tell you one example of a recent interaction that we had with a medical oncologist at our center. And she was telling us when she's looking to whether she can prescribe therapy for a prostate cancer patient, such as radiopharmaceutical therapy, she looks at their hemoglobin levels. And if a hemoglobin level is too low, that's a problem. But she was telling us if the hemoglobin level has stayed consistent, even if low, but consistent in the course of other therapies, she would be more confident to put this patient in therapy. So we tend to not even track these numbers, even in a scalar format, let alone in a vector format and in the context of previous therapies. And these are clearly in the context of clinical decision support, things that really need to be happening. There's a famous sort of an article, it's like a two-page essay or blog by Rich Sutton, who was a Canadian computer scientist and worked a lot on reinforcement learning, one of the founders of reinforcement learning. And this influential blog, he kind of makes the important point that the bitter lesson has been that we sometimes have tried to think we understand what the human mind does and develop algorithms that does that, but really the techniques that have really focused a lot on scaling computation, they have done well. So the bitter lesson is that progress comes not from directly imitating human thought, which is tremendously irredeemably complex, but from leveraging computer power to discover solutions. So you could argue in the neural sort of net and big data, big computation world, we're sort of perhaps following this. But let's come back to that point. So present approaches to medical imaging, actually, they don't involve massive amounts of data because of a number of limitations. And even on the human-centric approach that some previous techniques have done in the past that Rich Sutton would say is not going to be successful compared to big scale data type of works. We're not even doing that because human-centric approach would be involving how a human thinks, but in our case, that's how a physician thinks, not how me as an AI developer think. So usually we project how a radiologist thinks on our own minds, and then we develop things. So we're not doing anything in that sense correctly. And so we AI developers commonly take on the role of the physicians. We work on a problem that we think they find interesting, sometimes being surprised at the end of the project that they don't even find this to be interesting, completely oversimplify or invent what we think they are thinking, right? And then we attempt to replicate them. And commonly we provide a solution that does not work well enough as a result. Or even if it works by our own criteria, that's not even interesting to the physicians. So we have serious problems. So in the entrepreneurial world, startup world, there's this book that is kind of popular, the mom test. Ask questions from your clients in a way that even if you were asking your mom questions, she wouldn't be overly nice to you, because the idea is that often people are overly positive to you if you ask them questions in a typical way, partly because they want to be nice to you, they don't want to disappoint you, and partly because maybe they want to get you out of their way, and they're like, okay, fine, whatever, move on. And so for us to truly interview, right? So a physician in ways that are deep, and we're not just looking for compliments or vague ideas, right? Trying to really understand understand what they're doing, enter interview mode with our physicians, right? And with our knowledge users that will be using the AI is super important. So let's talk about physician in the loop AI. And so with current limited data, our models are limited. And if presented as final solution to clinicians, even if they're interested in the problem that we think is important to them, they will likely be met with frustration, and we will likely be met with frustration and rejection by them because the performances are not that great. And so alternatively, we can use physician in the loop AI to actually improve a model over time. We're not going to have a perfect model. And so this hit me, for example, when I was having a conversation with one of our close physician collaborators. And for example, he was saying, listen, it's unlikely that prostate cancer metastasizes to the brain. So sometimes we see like something, light up in the brain. Now, given the limited data that we have, we don't have that knowledge. But if we have a model that sort of works, and then we create an AI solution, and then we work with our clinicians in a physician in the loop sort of style, that over time, those deeper knowledges that they have not been incorporated in our previous limited data will be incorporated in a sort of physician in the loop AI. We will build models that are better and better. But that requires an understanding and a tango between the knowledge developers, the AI developers, and the knowledge users, the AI users. This kind of a language is an implementation science language, which we'll talk about later. So there's different ways for human and AI sort of interactions, active learning, where the machine selects the subset of data that it thinks that it's most uncertain about, and then the humans would sort of help the most. Their time would be best spent on that subset. Interactive machine learning and machine teaching. And I'll go somewhat quickly over some of the, given the limited time that I have, over some of these slides, but they will be on YouTube, and people can go back in more detail and look at these things. So this kind of, you have a super early sort of a physician in the loop proposal here for content-based retrieval. And the idea here was that the physicians can delineate, for example, pathology-bearing regions and landmarks. For example, you want to do a search, like a Google equivalent search of other cases that are similar to your case. But as physicians enter the loop to add more landmarks and sort of notations, this allowed this retrieval system to sort of work better. Here's an example of a framework that integrated expert human knowledge using explainable AI to guide models towards clinically relevant regions. Another one where sort of you're looking at agentic AI, interactive agents, and two interesting things. First of all, a short training period of even 1 hour was enough to equip the physicians with enough knowledge to propose relevant and feasible ideas. Now, interestingly, also, this makes physicians interested in designing, right? And so as you're interviewing, as you're talking to physicians, you're learning from them, but you're also making them more interested in the project that you're having, which is an obvious statement in the field of implementation science, as we will talk about later, but unknown to many of us in practice, many knowledge developers. Another example here where an intervention block, an innovative algorithm has been developed where there's an intervention block that allows the human intervention during the test time, for example, that you can look at. In our own lab, we're looking at gaze-guided clinician in the loop platform for image segmentation, where you could do faster pointing to the regions of interest through the human gaze, the clinician gaze, and this could allow you to do faster semi-automated detection segmentation. But also the idea is to allow that interaction to become more readily present in different phases of interacting with an image. So how do we actually make AI models adaptable to the dynamic reality of medicine? So physician involvement improves trust, but how do we do this? So specifically, I want to talk about physician in the loop active learning, which is a very important area. So with active learning, the problem, however, is that when you get newer and newer data to enter, and so, for example, that the machine is uncertain about, and it says, listen, if somebody annotated this, I would get a lot more certainty, or I could improve my performance more. So more data come in, but then we have a problem that many of you would know about, the problem of catastrophic forgetting, and that there's a lot of fascinating research happening in this area, that as you learn new data, you could forget the older data. So with continual learning, we can provide solutions around this continual active learning so that people have been looking at. So again, combining active learning with continual learning to tackle things like catastrophic forgetting. This is a paper recently published in American Journal of Röntgenology, and so you have the radiology workflow, the annotations are happening, more data is added to the training pool, the models updated through active learning, and then you've got a new model, and new samples can be sent back for annotations, etc. So one interesting thing we found through a lot of interactions with our physicians is that not only do we need physician in the loop AI, we need personalized physician in the loop AI, which means different physicians like to work differently on interactive AI. And so you have to develop interfaces and also AI thresholds based on their preferences. For example, different clinicians may want different sensitivities at the voxel level for, let's say, some kind of a detection task, because different false positive voxels, this is an example, below the diaphragm can affect staging in lymphoma. So you actually, not only do you have to have a good interface, you have to have an interface that is tunable for the preferences of the individual physicians. It's not straightforward, but it needs to happen. You need physician-centric designs, right, for ease of use. And of course, there's a lot of interesting things that we could learn from the world of the human-computer interaction, HCI, and a subset of it that is user-centered design, UCD. PACS integration is very important, and implementation science techniques, which we'll talk about later, to really allow us to deploy these techniques in real-world clinical settings. So here is a challenge that I propose to every single person, including trainees that are working on an AI project. Design, think about, you don't have to actually do this. Actually running a clinical trial is very, very difficult, but design, write on paper, a clinical trial that would test the added value of your AI solution. What kind of a clinical trial would you have to run, right, in your network, with physicians running it, of course, that would test the value of your AI? There's just so much value to doing this exercise. We've done this in our lab. It's very interesting to really, really think about this. This pushes you to interact with clinicians in asking the right questions. So this is integrated knowledge translation, which is very important when from the get-go, from the beginning, problem definition, you start working with physicians, right? So you co-create the solution together, including from the very beginning of the problem definition. This allows you to understand how actionable, right, usable, useful your AI is going to be, and truly fine-tune the task to something meaningful. I'm just going to show you one example. Here's a PhD student in our lab, Monica, working on a particular project, radiomics-guided therapy of follicular lymphoma. So she went through this exercise, sitting down, problem definition itself coming from a radiation oncologist. Do we do curative intent radiation therapy on this particular subset of patients, limited stage follicular lymphoma, stage 1 and 2, or do we do adjuvant chemo and immunotherapy, right, in addition? So she comes up with an objective, inclusion criteria, exclusion criteria for we're not actually running this clinical trial. We're saying if our technique is successful, how would we actually test it in a clinical trial? And it's a great exercise to do, and ultimately think about what is going to be impact. The study may show some benefits in patients receiving treatment as determined based on your radiomics or AI models. And so to allow you to decide, for example, whether you're going to put the patient on radiation therapy or radiation plus immunochemotherapy. Okay, this is just an exercise. But everybody, I believe, should really try to do this. So having seen the promise of active and physician in the loop learning, let's now move towards foundation models, right? So, can they live up to expectations? So, of course, in foundation models, we have very large multi-purpose training data sets, large model sizes themselves, computational resources, some kind of self and semi-supervised training, and adaptable to new tasks. So this typically involves getting lots and lots of data, but that lots and lots of data, again, is not at the scale of natural scenery data in reality, right? So we've got a situation again there. And sort of doing downstream tasks and training and things of the sort. But when you look at the actual performances of medical imaging foundation models, not non-medical imaging, but medical imaging foundation models, sometimes you would be surprised that the performances are actually not that impressive. And so you would expect, because you have a lot more data sometimes than you typically have. Here is of the order of tens of thousands, in this case over 100,000 CT. But once you look at the actual performances, organ specific, so if you randomly initialize a model and then do downstream training, so this would be your sort of baseline, and then you do the foundation model based on significantly pre-trained foundation models. Look at the performances. They are not really that different. Even though, there's a claim or a statement that there's a higher mean dice coefficient of 0.8981 than the baseline 0.8959. But look at these differences. Even if they're statistically significant, they're definitely not clinically significant. They're nowhere near clinically significant. And so we've got serious issues there. And as you go through the literature, you ultimately arrive at there's need for even more data curation, multimodal integration, and physician in the loop validation, as people are talking about. Also, for even slightly increased performances, sometimes you have significantly higher usage, like more energy that's being consumed in some of these models. You may then think, how about not pre-training on like ImageNet type of things, but pre-training on a massive, like a medical imaging sort of a data, so like radiology net. In those cases, again, so far the performances are not that better. Maybe there are some advantages in resource limited settings. This is in histopathology. Again, pre-training on histopathology data sets as a foundation model that did not show significantly improved performance. Another example, similar things, only modest improvement. So something is missing. And the sort of statements that I'm making here are that what is missing are the serious problems that we've been talking about in the course of this presentation. And so so we really have to rethink and redo certain things. So, you know, can we, for example, massively increase the data that we're having? And this is certainly something that should be happening. If somebody once told me, physicists, when they started working on the CERN type of, projects, massive projects, many people would come together, publish a paper with thousands of people on it. Why are we not doing that in the foundation AI world in medical imaging, right? A great question. Part of the issue, of course, is data sharing is limited. If you look at this publication, only 2% of AI articles shared both code and complete experimental data. Only 55% of papers on machine learning for health, considering this particular study, use public data sets compared to 90% computer vision. So we have limited access to public data sets, to massive public data sets, and something needs to change it. Now, these challenges, such as the one I have the pleasure of speaking to as a keynote speaker, these kind of efforts, my hat's off to the organizers, right? So when people, I have the utmost respect for people who do this, who run data challenges, because they add data, they add public data to the community to do further development. So we need a lot more of these sort of efforts and sort of to scale the kind of and to incentivize public sharing of data. We could also really work on not just data sharing, but data generation. Could we use AI itself to generate more data? For example, reports for patients, which of course would be in an interactive way with clinicians, and then generate more data, more reports for the patients, working closely with clinicians to speed up the process of data generation, including non-medical imaging associated sort of data that are very important. Very importantly, if you're going to do physician in the loop AI, you need to have platforms, right? So you have to actively think about, in any lab that you're in, what is going to be your physician in the loop AI platform? Who are your partners, and what platform are you going to use to work with them, right? So there's a lot of sort of products that are out there, right? So there's a lot of validation studies going on right there, but there's still continued lack of evidence on clinical and socioeconomic impact. So people are doing stuff, they're evaluating stuff, but things are not really making it to them. So these are all most likely related to some of the serious problems that we're raising here. So, there's people have tried to come up with potential platforms like MONAI. Many of you are familiar with this, the MONAI label framework for AI-assisted interactive labeling of 3D medical images. There's other ones that are out there. The idea at the end of the day is you need to come up with platforms, user friendly, physician in the loop solutions that will allow you to deploy your AI, even if it's not perfect, and it will not be perfect, and then over time, iteratively to improve these models with assistance from the physicians. Now, we really have to take a step back. Is it really physician in the loop AI, or is it something else? So we've had some discussions in this paper that we had, some kind of an AI task force in our society that we had, and what does it even mean to have trustworthy AI ecosystem? And we identified 12 very important components that makes a trustworthy AI ecosystem. Trustworthy in that ultimately it can be trusted on in risky situations, and medical imaging is certainly a risky situation for the patient. You're making an important life-altering decisions for your patients. So two very important ones were human agency. Ultimately, AI systems should empower physicians, allowing them to make better informed decisions, fostering their autonomy. Oversight was an important one, for example, that needs to be there. But of those 12, I just mentioned these two. So we really have to think about this perhaps differently. Instead of, especially in the context of clinical decision support, naively calling it physician in the loop AI, where the physician is just standing on the side, just looking over. No, really, what we really ultimately are looking for is an AI in the loop physician in our ultimate clinical decision making. Now, of course, for certain subtasks in that entire loop, we may want to use AI in the physician in the loop AI. For example, maybe the AI can help us find certain tumors faster. Maybe it can help us measure the volume of tumors faster. So for those, you would be having some kind of a physician in the loop AI to improve those specific tasks that might be automated better, right? But ultimately, in the clinical decision making, ultimately it's about human autonomy. Ultimately, it's about the humans making those decisions. And so in that sense, what we really are aiming for is AI in the loop physician. So again, going back to those exaggerated claims, which I believe highly damage progress in our field, that, oh yes, yeah, this new generation is going to replace you as a radiologist, and you're not going to, as a human, as anything. It's a totally different one. So I was once attending this MICCAI conference in Vancouver, my home city, and Jan LeCun was giving this talk, and I was just minding my business listening to him. And then he sort of said at some point, oh yeah, AI is going to exceed human intelligence in any sense of the word. And that kind of got to me, that kind of statement. And we've had these exaggerated claims a lot. And it just bothered me to the extent that I ended up writing a paper which was published in International Philosophical Quarterly, and sort of I read it here. We make the claim that AI machines do not compare with human beings in task performance. We explore how the human being interacts with the world, with beings and the being of beings, and how it circumspects reality. We argue that AI arrives on the scene too late, or just on time enough to perform a given task assigned to it, as an extension of the human being. We discuss that it is short-sighted to claim that AI will exceed all levels of human intelligence. We focus on works by continental thinkers. Martin Heidegger was a very important one, and based on his thinking, some philosophers were really saying that previous generation AI would not work as well, and it did not, because it was oversimplifying what human does to logical thinking, and humans are embedded in reality. It's a being in the world, and so again, we continue to think we know what humans think, and sometimes so there's a lot of when experts in a particular field start to make opinions about fields they're not experts in, we have a lot of issues. So was recently attending another meeting where Rosalind Pickard, she actually made this point well and much better. It's something that I would agree with a lot more, that ultimately we really have to think of AI as an extension of a human being, and a human being is one that defines new paradigms, and AI would be an extension of a human being. So ultimately, for clinical decision support, instead of physician in the loop, we need AI in the loop physician, AI as an extension of the human being who has autonomy and is the one, meaning the human being is the one that is deploying the AI. Okay, so how do we do this? How do we truly engage with clinicians? How do we truly um, um, develop things, problems that are very important, and also really turn that evidence into routine deployment in the clinic. So there's a famous paper or highly cited paper. It says the answer is 17 years. What is the question? And the question is, how long does it take to take research into routine usage, right? So there's so that's the translational gap. And there's other studies showing that it takes from publication of something that we know it works to actually making it deployed in routine sort of usage, it might take an average of 15 years. So 15, 17 years, all these things. So evidence, even if you have evidence something is good, that doesn't mean you have desire to use by those who are going to use it. So implementation science itself is an evidence-based approach to translate evidence to practice. So even if something works, we know it works. In a limited setting, we've tested it, it works. You need an evidence-based way to take it and have people actually use it because they may not even want to use it. So we have an interview, sort of a discussion and interview in our YouTube channel with Dr. Fayaz, and we even recently published a paper or wrote a paper. It's accepted, will be published soon. What is implementation science and why it matters for bridging the AI innovation to application gap in medical imaging? So implementation science is this scientific study of methods to promote the uptake of research findings, highly related to knowledge translation, which is really the process of moving that knowledge. They're sort of highly related terms to each other. We have end of grant, or you could call it end of research knowledge translation, where you develop your technique and then you find ways to deploy it. But very interesting, there's integrated knowledge translation, where knowledge users are engaged throughout the research process, including the problem definition from the very beginning to co-create and define and co-create the solution together. So you co-identify the clinical need, you start to develop the solutions, right? And then you're constantly integrating or interacting between the knowledge user and knowledge creator for all these stages, validation, clinical deployment, and post-deployment monitoring. So very, very important area. So even when it comes to evaluation, we have to be very careful that often many things that we publish, like the performance of a segmentation method using some kind of a dice score, that's a very sort of baseline, important, but baseline proof of concept evaluation. Then you move it up to something a little bit more technically related to what you care about. For example, if you're measuring the volume of a tumor, then you are measuring the tumor volume values. But you got to move up. You got to come up with clinical metrics. Does my molecular tumor volume, sort of automated AI solution actually prognosticate patient responses better, right? So this is all evaluation. We're not even at implementation, right? So implementation is when you move up. You haven't just done a study on could your AI solution work or does your AI solution work? These are efficacy and effectiveness. Ultimately, the challenge is to making your AI solution work. And that's the field of implementation, research, implementation science to really allow you to take your solution, even if you have evidence for it, to actually deploy it. So again, first you have to work on reason to use, but then you have to tackle other barriers like means to use. Do you even have the infrastructure to deploy what you need? Do you have the resources or method to use? Do you have the efficiency or the workflow training that will allow the people in the clinic to use it? And ultimately, do you even have the desire to use? Even if everything works, even if everything is ready to use, maybe the physicians will not use it because you haven't motivated it enough. Maybe they're worried about legal challenges, right? All kinds of hurdles that might be out there. So then you have to really motivate and inspire and have to understand in your interactions why a clinician would want to use these solutions. So ultimately, it's about collaborations, partnerships. It's about knowledge creators and users working together, sometimes with the help of knowledge brokers, creating those alliances and coalitions to ultimately co-create and co-implement, perhaps in the sense of integrated knowledge translation, the solutions that you want. So summary of key points, adaptation matters. You need serious consideration of physician in the loop AI, active learning, continual learning strategies. You need foundation models that are perhaps rethought because existing models, some of them in medical imaging, are not performing that greatly. And so we have to think about cost, data, the modest gains, where are they coming from, and what are the challenges? Data. These challenges are helping. How can we create more and more medical imaging data, put it all together? And remember, it's not just about, when we say medical imaging data, we should always remember as we were making the point, it's not just imaging data, right? So it's definitely has to have non-imaging data in there. Existing models underperform due to limited imaging data, limited imaging data, limited computing resources. So we need innovative algorithms that can learn more effectively. And this is an open area of research and investigation. Platforms, we need platforms that enable translation, that further development and things of the sort. We need to really think about implementation science, implementation scientists. We need to enter deep interview modes, and we need to really understand these fields better. Ultimately, not all AI are created equal. Our present medical imaging AI efforts tend to be highly problematic. They need much more serious co-creation of solutions towards AI in the loop physician. Some acknowledgements here, very helpful discussions with a number of colleagues here, members of some task forces, and some grant support. And you can find some videos related to these discussions in our YouTube channel. Thank you very much and have a great day.